Welcome to the course on numerical linear algebra and application. Today we are going to have 42nd lecture of this course. Before going to the contents of this lecture, let us quickly recall what we have learned in the previous lecture. In the previous lecture, we have seen that the iterative techniques plays a vital role in scientific and engineering applications. In the iterative methods, we have seen how the convergence, stability, consistency takes place as compared to direct methods. So in continuation to that, we are going to have some few more examples of iterative methods in this particular lecture. Let us quickly recall once again the Gauss-Jacobi iteration. Look at this. We have A11 x1, A12 x2, A1n xn is B1. Similarly, A21 x1, A22 x2, A2n xn is B2. An1 x1, An2 x2, Ann xn is Bn. So altogether we will have n by n coefficient matrix, and we will have x1, x2, xn vectors, and B is equal to B1, B2, Bn vectors. We assume that the quantities Aii in the above system are elements. The equations may be written as A11 x1 is minus of A12 x2 plus A13 x3, like that A1n xn plus B1. Similarly, A22 x2, A21 x1, A23 x3, like this, A2n xn plus B2. Like that, we will have Ann xn is minus of An1 x1, An2 x2, Ann minus 1 xn minus 1 plus B of n. So the Jacobi method and Gauss-Seidel iteration method will be defined as x1 of k plus 1 will be equivalent to, that is pushing all the right side, and similarly while doing x2 k plus 1 pushing all the things on the right side, similarly pushing the xk plus 1 and rest are all pushing on right side. This is valid for every k is equal to 1, 2, etc. Remember that A11 we ensure that it is free from 0, A22 ensure that this is from 0, Ann it is ensured that it is free from 0. Since we replace the complete vector xk in the right side of equation 1 at the end of each iteration, this method is called the method of simultaneous displacement. That means x11, x21, x31, so on and so forth, we will be doing at one time. That is why it is called simultaneous displacement. So in the matrix form, we will write it as x of k plus 1 will be equivalent to minus of d inverse L plus u times of x of k plus d inverse of b. That will be equivalent to h times of x of k plus some constant C, where K would be from 0, 1, 2, etc. Where this H is equal to minus of D inverse L plus U, where L plus U is equal, where C is equal to D inverse of B. And L and U are respectively lower and upper triangular matrices with 0 diagonal entries. And we will write this A as L plus D plus U. Lower triangular matrix, diagonal matrix, upper triangular matrix. So which we can write it as xk plus 1 will be equivalent to x of k minus I plus D inverse L plus D x of k plus D inverse of B. X of k minus D inverse of L plus D plus U x of k plus D inverse of B. So ultimately we will end up with x of k plus D inverse of B minus A x of k. Or we can write this as V of k is equal to D inverse of R of k, where Vk is equal to x of k plus 1 minus x of k is the error in the approximation, and Rk is equal to R of k is equal to B minus Axk is the residual vector. We may write the above equations as D of Vk is equal to R of k. We solve for Vk and find x of k plus 1 will be equivalent to x of k plus V of k. These equations describe the Jacobi iteration. These equations describe the Jacobi iteration. Now let us look at into the few examples where we can find out the practical applications. Look at this, 4x1 plus x2 plus x3 is 2. x1, 5x2, 2x3 is 6, minus 6. x1 plus 2x2 plus 3x3 is minus 4. Look at this. If you look at this, a11 is 4, a22 is 5, a33 is 3. So 4 is obviously greater than or equal to 1 plus 1 in the first row. 5 is greater than or equal to 1 plus 2 in the second row. 3 is greater than or equal to 1 plus 2 in the third row. So that means diagonal dominance is obtained. So using the Jacobi iteration method, given equation 2 and its error is give equation 3, we will take the initial approximation as 0.5 minus 0.5, 0.5. Take the initial approximation. So the choice of the initial approximation is very crucial. How you are choosing the initial approximation, if not given, depends upon how closely you can expect the solution with minimum error. So, and perform if 3 iterations in this case, so you will approach as x of 1 is 1, x of 2 is minus 1, x of 3 is minus 1. So, in the course of time, when you transform the elementary operations, so you get what we call lower triangular matrix. You see here, this is the main diagonal, subdiagonal, subdiagonal. These are all zeros. Similarly, the matrix D is the eigenvalues sitting on the diagonal elements. Upper triangular matrix is, these are all zeros, lower will be 0, and this is a non-zero. and H is equal to minus of D inverse L plus D. So this will be equivalent to minus of 400,050,003 whole inverse multiplied with 011, 102, 120. So if you simplify, you get like this. This is the main diagonal and these are all zeros. These are all zeros, and you get the matrix C as like this. C is equal to 1 over 2 minus 6 over 5 minus 4 over 3. Therefore, the Jacobi iteration method gives, it would become like this. That is, x of k plus 1 will be equivalent to 0 minus 1 over 4 minus 1 over 4 minus 1 over 5 0 minus 2 over 5 minus 1 over 3 minus 2 over 3 0 multiplied with x of k plus this vector 1 over 2 minus 6 by 5 minus 4 by 3. So if you start with initial vector, x of 0 is equal to 0.5 minus 0.5 minus 0.5 transpose. Alternatively, we can write it as x of k plus 1 will be like this. 1 by 5 times of the constant you push to the right side and x1 of k minus 2 x3 of k. So x3 you get as 1 over 3 times of the rest of the elements. So starting with x1 is equal to 0, x2 is equal to minus 0.5, x3 is equal to minus 0.5. So you get a vector like this. And using 3, we could able to achieve this x of 0 as 0.5 minus 0.5, 0.5 transpose. So when I try to compute this error, that is R naught B minus AX of 0. So you do arrive this value 1 minus 3 minus 2. And this V of 0 is nothing but D inverse of R0. So you get like this, D inverse of R0, so you get a vector like this. So therefore, x of 1 you could write it as 0.75 minus 1.1 minus of 1.1667 transpose. And for k is equal to 1, you write R of 1 is B minus AX of 1. So this is the matrix B. This is the matrix AX of 1, so you could arrive these values 1.2667, 1.0834, 1.9501. And V of 1 is equal to D inverse of R1, so D inverse is this matrix. So this is the main diagonal entries, zeros, 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 multiplied with R of 1, which will give you this matrix. So therefore, x of 2 turns out to be 1.0667 minus 0.8833 minus 0.85 transpose. And for k is equal to, you compute this, that is B minus AX of 2. So you get the column like this, minus of 0.5335, minus of 0.9502, 0.7501. So ultimately you do end up with x of 3 like this. 0.93333 minus of 1.0733 minus of 1.100 transpose. Note that we obtain the same result from both the techniques. Either way, we could able to achieve the same value. Now, in the similar fashion, if you look at the Gauss-Seidel iteration method, we now use the right side vector of 1 and the available values from the present iteration. So, whatever is being available, we use it and we will try to iterate it. That means x1 of k plus 1th iteration is, so push everything to the right side where this a11 is assumed to be free from 0. Similarly, xk plus 2o would be like this, where this a222 would be free from 0. So, like that, if you continue, xn of k plus 1, which turns out to be this thing, ann is free from 0, ann is free from 0. So, which may be rearranged in the form a11 x1 of k plus 1 is minus sigma of I is equal to n a1i xik plus b1. a21 x1 of k plus 1 plus a22 x2 of k plus 1 is minus summation I is equal to 1 to n a21 xi of k plus b2. Like that you continue, so you end up with an1 x1 of k plus 1 plus etc. ann xn of k plus 1 is bn, where ann is free from 0. Since we replace the vector xk in the right side of 1 element by element, the method is also called successive displacement. That means whatever is being available in the first iteration, first element, let's say x1, we are using in x2 updated approximation, and whatever is being available x2 we are using in the next iteration. We keep on doing like this. That's why it is called successive displacement. Simultaneous displacement and successive displacement, we see the difference. So, in the matrix notation, we can write it as d plus l type of times of x of k plus 1 will be equivalent to minus of ux of k plus b, or we can write it as x of k plus 1 will be like this, where this h will be equivalent to minus of d plus l whole inverse of u and c is equal to d plus l whole inverse of b. And from the equation 5, it can be written as x of k plus 1 is x of k minus I plus d. D is the diagonal, L is the lower triangular, and d plus l whole inverse will be added up with d plus l whole inverse times of b. So, ultimately we will end up with an expression like this, where this v of k will be d plus l time inverse times of r of k, and this v of k is xk plus 1 minus xk, and the residual is very, very important. R of k is nothing but b minus ax of k is the residual. We may rewrite the above equations as like this: d plus l times of v of k is r of k. These equations describe the Gauss-Seidel method in the error format. In example 6, solve the system of equations, that is 2x1 minus x2 plus 0x3 is 7, minus x1 plus 2x2 minus x3 is 1, and 0x1 minus x2 plus 2x3 is 1. Using the Gauss-Seidel method given in equation 5 and its error format given in equation 6, take the initial approximation as x0 is 0, perform 3 iterations. That is what the question has been asked. So, If you write this equations, d plus L is nothing but 0 2 0 0 minus 1 2 0 0 minus 1 2, and upper triangle matrix U is equal to 0 minus 1 0 0 0 minus 1 0 0 0. The Gauss-Seidel method gives you x of k plus 1 is equal to minus of d plus L whole inverse u of xk plus d plus L whole inverse times of b. So we get d plus L whole inverse is this one, and ultimately you could arrive this matrix. D plus L whole inverse times of u, you do arrive this matrix. Since L and u are the lower and upper triangular matrix, existence of inverse is not a big issue. So if you take this d plus L whole inverse times of b, you get a matrix like this. Therefore, we obtain the iteration scheme as x of k plus 1 is equal to, that is the main diagonal, subdiagonal, super diagonal, rest are all zeros, times of x of k plus the right side vector. So if you start with the 0 as initial vector, you could able to arrive this value x of 1. Similarly, x of 2 will be this, because you are using the successive displacement. That means the whatever x1 is there, you are using it, and obtaining x2, again what is x2 you are using, like that you keep on doing. So therefore this change will be best approximation. So it is updated. So obviously when you compute this error in this process, it should turn out to be lesser than what we did in the previous case. And in fact it is true, it would be less. So if you keep on continuing like this, in the course of time, the error will become smaller and smaller, then you get the better convergence. Look at this, V0 will become d plus L whole inverse times of R of 0. So D is the matrix, D plus L is this matrix, main diagonal, 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 zeros, multiplied with R0, and you get this. So therefore, the updated x of 1 is x of 0 plus V0, which turns out to be like this. So therefore, when you compute this error, R of 1 will become B minus AX of 1. So you get B is the matrix and A is the coefficient matrix. X of 1 is already computed over here. So we may end up with the error like this in the first iteration itself. And V of 1 is D plus whole inverse times of R1. You get like this. And second iteration, if you do it in the same fashion, you do end up with these values. Similarly, compute the error in this case. R is equal to B minus AX2. You get like this. Look at this. 1.375, 0.6875, 0. In the previous case, it is bigger values. So it's keep on reducing it. So if you continue like this will become very, very smaller value. Then we conclude that the error will become very small values. So if you do the third iteration in the similar fashion, right, you do get the error like this. So in fact, the x3 will get improved, and still if you compute R minus BAX, here it should become much smaller than what we did in the previous case, right? Okay, so what we learned in this today's class is Gauss-Jacobi method, Gauss-Seidel methods. So many examples we did it in the previous class and also today's class. So and we also have seen simultaneous displacement and successive displacement. So obviously successive displacement will play a vital role and it will fetch you the best approximation with minimum error in general. Thank you very much for listening to my class, and I'll stop it over here. Thank you very much.